Well, hello everyone. Welcome to Harsh IT Lab. Harsh Verma this side, and today we are back again with our book Network Warrior. And topic for the day is routing and switching, which you can see over this thumbnail. So, without any further delay, let's quickly go to our book. And for those who don't know that we are following a book known as Network Warrior, let me show you that. So this is the book, and this book is written by Gary Dono. Basically, this book focuses and outlines the practical lessons that we missed during our CCNA preparation. Because despite having some physical lab topology exposure or practical exposure, CCNA most probably requires the theoretical learning. So we used to miss some details, and we will get back that details in this book. So I'm not covering this book cover to cover, but actually pointing out the things that you must need to know in order to get success in your academics or in your job profile. So without any further delay, let's SSH into my phone, which I've already done, and start the topic, which is routing and switching. So we know there are two kinds of devices in the network, most commonly known devices. First is router, and second is a switch. And the most common difference that switches usually have larger number of ports or have a higher number of ports than a router. Router usually have 4 to 8 ports, while switches comes into up to 48 or sometimes even more. Okay, so what is difference between routing and switching? The basic concern. Basically, routing is the process of choosing path and forwarding packet to destination outside the physical router. So basically, this statement tells that in case of router, one port is connected to some other network, while other port may be connected to a different WAN or LAN. So there may be different kind of network, and the amalgamation or the interconnection between network is performed by the router. While the switching is the internal forwarding of packet between interfaces. For example, the endpoint devices like not a smartphone, but you can connect a smartphone to a switch using an Ethernet adapter. But laptops, desktops, servers, etc., all are connected to a switch. And we do have hierarchy of switches. The basically endpoint devices are connected with access layer switches. So switching is the internal forwarding of packet between interfaces. Switching is as simple as it gets. But there is much more to switching. Because routing is interconnection of route, there is something for a moment of time, something is happening inside of router. There is something called what to say, internal forwarding of packet between interfaces, because router also has interfaces and it is forwarding the packets based it basically go through a decision tree to make sure which packets to forward into which interfaces, and that minute process is also known as switching. So don't confuse yourself, we will get through it. And because the topic is too large, I actually feel like I should make this video into two parts. So consider this as the part one of the video. Okay. Now switching is mainly divided into two types. In this case, we are actually talking about the switching that happens inside the router, because router also have multiple interfaces. Okay. So the first variant is process switching, while the second one is interrupt context switching. Without taking pressure on your mind, first understand the process switching, and after we go through it process switching, we will automatically able to handle how interrupt context switching is different from it. Okay. Or by the way, interrupt context switching is also subdivided into three more types, which is fast switching, optimum switching, and SEF. This Cisco special version, Cisco Express Forwarding. And actually this is another reason to love the Cisco, because you always find in every domain there's an innovation that has been led by Cisco. And for that innovation, the research and development, I love this brand very much. Okay, so without any further detail or further disclaimer, let's go to the common steps in switching process. Basically the decision tree between passing a packet from one interface to other. What will happen? It is checked whether the destination is reachable, it is determined whether the next hop or egress interface, matlab which is the next hop or the egress interface. And finally, the rewriting of the MAC header is done, because for the next hop you have to rewrite the MAC header, and the layer 2 will further determine how to reach the packet, which will use the layer 1 basically cable. It may be fiber or Ethernet. So that's a too much basics. Okay. So before switching, there's a thing called IP input, or to expanded version, we can say IP input process queue. We have to study it. We have to get a hold of it in order to understand or even understand the process switching. Because after that, we will continue to the interrupt context, then fast optimum and Ceph. Okay. So the IP input queue is a software queue serviced by the router's IP input process. Packets that cannot be switched by a faster mechanism are placed into this queue, and the IP input process performs the following task. So basically what we are saying, that IP input queue can be understood like a flow chart or a proper checklist that need to be done in order to pass a packet. If if and only if the packet cannot be switched by a faster mechanism, and here the faster mechanism is the second type of process switching, which is just mentioned here, interrupt context switching. And in this there are fast switching, optimum switching, and Ceph. So when we are not using these kind of technology, the interrupt context switching, we will use the IP input process queue. And because we are not studying the interrupt context switching right now, the process switching is going to take place. Okay, so what are the mechanism? The first is packet validation and sanity checks. Basically, because every packet contains some type of check, some integrity checks, so we have to first validate whether the packet received is actually it is as intended. Because if it's not, then there is no a better way, or there is nothing worth to actually waste our CPU cycles to process that. So it's immediately discarded. Next is IP header examination and destination address extraction. So basically, IP header examination means we are talking about layer 3. We extract the destination and source IP addresses. Uh, because of source IP address, basically the source IP address, yes, we get to understand that from which device it came, and because of destination, we understood that on which device actually it is destined to, because it will help us to make the routing decision. Next is routing table lookup. In order to confirm the routing decision, we have to check our routing table, also known as routing information base. Finally, the access control list processing, if configured, or a route map processing may come in between if configured, because these are variable scenario. Not every network admin must have configured ACL or route maps. Okay, so your mileage may vary. Next is policy routing and other software based feature processing. So basically it is talking about the route maps or any kinds of tagging or interface change, etc. Because in the last video we have studied that route maps overrides the RIB, routing information base. So we have to keep that in mind. Next is determination of next hop address and outgoing interface. So finally, after all these processes, there's one selected or elected that from which interface the packet will be redirected. Finally, because in each hop the layer 2 addresses, which is the MAC address, need to be overwritten, so it would be received by the uh, next hop device. So it is done in the step 7. And finally, the eighth step, the packet forwarding to the appropriate output queue. Because output queue have a separate buffer which stores the packet. It may depend, or it may be configured as per the flow control that is offered by your device's specific settings. So it will be placed in that queue. And IP input process is necessary to study, because the IP input process is basically the process switching. It is the core or essential of process switching. And we have to also study some key points. Because every packet must pass through the IP input process, the excessive use of IP input queue can result in high CPU utilization and reduced forwarding performance. because in order to forward each and every packet, we have to validate all these 8 steps. These 8 steps are not fixed or not static, it is dynamic. So there may be a few more steps involved depending on how your device processes the packets, or there may be less step involved if there are no filters or rule configured. So this can change, and because of this dynamic nature, the sometimes the packet may be processed quickly, sometimes delayed, etc. Now, well, let's talk about the process switching. We have understood the core mechanism behind it, so now we are able to get it very quickly and smoothly. So process switching is also known as software switching or slow path switching. And when a packet arrives to an interface, the network interface hardware generates a receive interrupt to notify the CPU. Basically, because we just understood the IP input process queue, now how the packet reached to that queue, we are understanding into this process switching whole context. Okay, so after receiving an interrupt, basically interrupt, what is an interrupt? So interrupt is an hardware or driver generated signal, but basically it's a signal sent to the cpu of the router or network serial controller to inform that new packet or new data is arriving and need to be processed. Now, the packet is temporarily stored in incoming interface buffer or input queue. Okay, so basically we have a buffer for receiving the packet. We also have a buffer to egress traffics or exceeding the interface, exceeding not egressing the interface. Okay, so in between two buffers, there's a process that sits, and that is the IP input queue process. Okay, now, this CPU services the interrupt and examines the packet header, determines the layer 3 protocol. Basically, it's the same process, IP input process that we just studied. So let me go through it quickly. I will definitely explain you if I find something new. For IP traffic, the packet is copied from the interface buffer to the system memory and placed in the input process queue. And now the next line will determine how input process queue works. So the input process queue removes the packet from IP input queue and performs a routing table lookup to determine the best outgoing interface, next hop address. Because the routing decision is performed by router for every packet, process switching consumes significant processor resources and introduces additional latency. So we have studied or discussed about it because it is a slow process, and it is also known as slow path, which is written here, and there's for a reason why it is called slow path. Okay, so the next is because the routing decision is performed by CPU for every packet, process switching consumes significant processors resources and introduce additional latency. So latency is also an side effect of this process switching. Now, during forwarding, the router may initialize or update the switching cache used by faster forwarding method. So this just hints to the next process interrupt context switching. Okay, I guess I am sorry, I get confused. What was it? Interrupt context switching. And where we were? We were here. Okay, so layer 2 frame header is rewritten with appropriate source and destination MAC address for the outgoing network segment. The packet is then copied to the output queue associated with the selected outgoing interface. The router recalculates the layer 2 field as required, including the FCS frame check sequence or CRC cyclic redundancy check before transmission, basically to validate the integrity of packet. The outgoing interface transmits the packet into the network. Since each packet requires a complete routing. Okay, so this is kind of repetition for the same thing. I will sort it down. And finally, the time is to talk about the interrupt context switching. So okay, so I guess we don't have to make another part for this video. So because interrupt context switching is way more concise to explain, because now we have until now we have understood how the process switching works. So interrupt context switching is way easier to understand. So let me begin it. So interrupt context switching or interrupt switching uses fewer process cycles to process the packet. And how it does so? It uses something called route cache. It could be understood or correlates to a DNS cache, domain name system cache, which is handled or stored by your endpoint devices. For example, we know that DNS uses to correlate between an domain name, human readable name, and an IP address. We know that. I hope that you also understand and know it. So instead of looking google.com, what DNS server does, it provides the IP address of the location google.com, the domain name google.com. Okay, how it does? Basically, it asks the DNS server, did you know the what is google.com, and it gives it's a public IP address or the reachable IP address of Google. That's it. So because in order not to ask the DNS server repeatedly again and again every time you perform a Google search, what our endpoint devices, for example our laptop or phones, do is to store a copy of that record that google.com is linked to this particular IP address in our offline system memory. By system memory, I not mean RAM, but the hard disk or space. Basically, it's a file where these kinds of records are stored. So basically, what I'm trying to say that route cache is just like that, like kind of a storage that stores that these kind of packets need to be forwarded from this particular route. If the same thing is getting repeated repeatedly, it will just look up the cache and proceeds with forwarding rather than full processing or going through full data, full R. Okay, now route cache is only updated after process switching. So in order to generate a route cache or in order to update the route cache, a process switching need to be performed. Now, route cache is not aware of the ARP. ARP stands for Address Resolution Protocol. So Address Resolution Protocol uh, basically it's a table that correlates between the MAC address and the IP address. So a particular device has a particular IP address, so basically establishes the relation between them. But because it is not aware of the ARP, suppose we change the IP address of a particular device, because this laptop has a MAC address of it and we can statically assign the IP address. Suppose we want two different IP addresses. Because the ARP is updated, but route cache is not aware of that changes in ARP. What will it do? It will lead to inconsistency in the case of such changes. So that's a kind of drawback of the first method of switching or interrupt switching. So there is resolution to this, and we will see up to Cisco Express forwarding that how this issue can be mitigated or resolved. So now we have understood what a interrupt context switching or interrupt switching is. Let's study the first type, which is fast switching. Fast switching is interrupt context switching is a method of interrupt context switching which utilizes the binary tree to retrieve the information from the route cache. Because I'm just guessing that not all you all guys are from a computer engineering background, but binary tree is basically like a tree structure in which everything has two value. Two value means basically everything can be divided into two types, and thus further division can be help to fast up the process. So basically read about this binary tree, go watch some short videos or YouTube long form videos to understand the binary tree completely. It's a very fun thing and it's a must know thing if you are into DSA. DSA stands for data structure and algorithms. So fast switching utilizes the binary tree, and binary tree ranges up to 32 layers. Why 32 layers? Because of the 32-bit IP address formatting. Because IP address is a 32-bit address, so it is a 32-bit 32 layers of a tree. Basically, tree like hierarchy. So router uses that to find the details from the cache, and it is faster than the raw process switching, but put a strain on router due to sheer binary tree size. Because it's a large size of binary tree, still put some loss, or you can say the process performance loss on the router CPU, but it is faster than processing or getting through the 8 hops. Next is optimum switching. It utilizes a multi-way tree. So multi-way tree is also a form of a algorithm or a data structure in which things are divided into the based of the repetition. For example, the first of few letters matches, it will create a tree. Actually, I will certainly link a video regarding the multi-way tree that I used to understand, because before actually reading this optimum switching topic, which was past few days, I have not heard of multiway tree until this point, despite me being in IT for around 2 years. So it's an interesting one. So I will link a video regarding the multivatry in the description. Go sure make sure to watch that. You will definitely get a few things to understand. Okay, sorry. So multivatry uses the value from 0 to 255, and each node points to another 256 node, making a total of 4 layers. So basically, it's a larger form of tree, but having lesser layers make it faster. And now we are talking about the OG, Cisco Express Forwarding, CEF. So CEF introduces the concept of try. And what is try? You also have to study that. So I have written the small definition of the try. In computer science, a try is also known as digital tree or prefix tree. Is a specialized search tree data used to store and retrieve strings from a dictionary or set. Okay, so using tree data structure, Ceph built something called forwarding table. So I have also watched a video about the try, how try actually used to store the strings. Okay, I will also link that in the video description. So using try data structure, Ceph built something called forwarding table. And forwarding table is like a RIB, routing information base, but it is much more simplified. So process can be sped up. Okay, so each node in the same static size contains no data. So instead of the node's position in try itself, a reference to another table, it also creates an adjacency table. So basically, two types of tables are created. From the routing information base, the original table, it creates a forwarding table. And in order to simplify that forwarding table, it also created an adjacency table, or what to say, adjacency table. So yes, that was the right pronunciation. I will definitely Google that and hear 2, 3, 4 times after the video. Okay, so forwarding table does not relates to process switching, making it more efficient to maintain because forwarding tables, it does not gets updated due to process switching, so it is way more efficient to maintain. Now agency table gets updated in case of app table, so it also resolves the issue of not getting proper update after an app resolution. So basically it takes helps from both adjacency table and the forwarding table. Adjacency table to find out whether the devices have been changed or is there any change in IP addresses, and forwarding table contains a copy of the routing information base. Okay, now Ceph also supports equal cost path load balancing. So basically Ceph can also load balance the traffic if the same device is connected on a ether channel or a channel bundle, so it can also load balance the path. Okay, and it also allows an option to set per packet load balancing in order to more uniformly balance the load. And I think this is the last line for the day. No IP route cache command is used to disable all sort of interrupt context switching at once. So it will disable the fast switching, autonomous switching, or SEP, Cisco Express Forwarding, at a single command. So why will we do that? Only in one scenario. If we want to debug something, because process switching utilizes the general CPU of the router, it will use and it will if we use that to process all the routes, we will generally able to see the debug messages or the error messages that we actually want to see if you are testing or researching something. So only in that scenario it will be advisable. Rest, use the what is it, the interrupt context switching as much as possible, because it will be better for both the lower the latency for your route and the freer the CPU or the more responsive router will be. And that's all for this video. I will make sure to add the link for the video that I mentioned in this venue. And thank you for watching. Thank you for joining.